Okay, so let us see now potential energy carried by wave. Now potential energy in this one is work done by tension in stretching the string. Okay, work done by tension in stretching the string. Now the question is how it is being stretched. Let us see. First, let's assume string is like this. Okay, but then string becomes something like this. Okay, it's the same length, but now just check it. If I take this portion, let's take this portion here. This length, because this is almost straight. This length and this length is almost same. Okay, but check this length now. This length here and this length here, is it same? This string here and this string here, is it of the same length or different length? Different length. This is a lot more than this. Okay, so what has happened in this particular portion, the string is stretched, whereas here you see string is having same length, but here string is stretched. So when this is stretched, tension doing this work. So we say potential energy is basically what? Work done by tension in stretching the string. Okay, now work done by tension in stretching the string, how will we writing? We'll be writing it as T into dx, or T into change in length, whichever you write, or dx is fine. Okay, now let's see how much change in length has come. Okay, what is change in length? So we'll say that increase in length minus original length. So if suppose that this is the original length, okay, this is x, and if I take this much portion only, it's like this. Okay, original length is this, and let's assume this is L, and let's say this is y. Okay, then we can say that this L square is actually x square plus y square. What is L? L is root over x square plus y square. And what is change in length? Change in length is L minus x. Okay, so what we can do? X square plus y square square root minus x. Okay, now from here, from this expression, this square root, I am taking x common. Take x common, so what will come? 1 plus y square by x square minus 1. Okay, now the question is, when you are having y and x, do you think that this y is very high? Too much? No. Is this x is very high? No. This is very small in case of a string. It will be very, very small because we are taking very, very small portions. So that means y by x value also will be very, very small value. So what we can do? We can open this with the binomial expansion. So see then, I am opening it over here. So we are trying to find L minus x. What's coming? Just check. X into 1 plus y square by x square to the power half minus 1 we have. If you open this with binomial expansion, if you remember binomial expansion, 1 plus x to the power n. When x is very small as compared to 1. Here y square by x square is very small as compared to 1. So how do we open it? We write it as 1 plus nx. Okay, so here also we will do this. This half will come over here. So this step here we will be writing as x into 1 plus 1 by 2 y square by x square minus 1. This minus 1 and this plus 1 is getting cancelled. Okay. Then what? What's coming? It's coming as this x we can multiply inside over here if you want. Okay. So x into 1 by 2 y square by x square. Okay, this is change in length. Now, what was the work done? We said that work done is t into x into half y square by x square. Okay, now this x is what? Change in along x axis. So better is, if you want to write it as dx, it will be better for us. So make it as all dx, then it will be clear to you more. Make it dy, this is dx, let it be d here also. Okay, here also. So what we have, this is also dx. So t dx, this is half dy by dx whole square. Okay, now t value we already know how, because in the last topic we defined the velocity of the wave as a function of tension. What it was? We define it as v equal to root over t by mu. That means t we can write as mu v square. T we can write as mu v square also. Okay. So we can write it over here. This is mu dx into v square 1 by 2 dy by dx. Now I am writing dy by dx. What is dy by dx? We know that y is a sine of kx minus omega t. So dy by dx will be what? A k cos of kx minus omega. Okay, we can put it over here. So it will come as a k cos kx minus omega t whole square. Okay, further 1 by 2 mu dx v square a square k square cos square kx minus omega t. Okay, now this v we can write as omega by k. So omega square by k square. Okay, so what will happen? This k and this k will cancel. We can write omega in place of that. Or you can say v into k. V is actually what? Omega by k. So v into k we can write as omega. Okay. So here v square k square we can write as omega. So this equation can be written as half mu dx omega square a square cos square kx minus omega t. Okay. So potential energy also we want to write per unit volume. So what we can do? We can divide it with volume both sides. Correct or not? So let's divide it both sides with volume. So see what's coming then. The potential energy per unit volume. So this is half mu dx omega square a square cos square kx minus omega t divided by volume. And what is volume? S into dx. This dx gets cancelled. Mu by s. This mu by s means what? It becomes rho. So this will become half rho omega square a square cos square kx minus omega t. Now see this one. This is exactly same as what we got for kinetic energy. This is the same expression. Maximum potential energy will be what? When this will become 1. That is half rho omega square a square. Minimum will be what? When this will be 0. So what will be average? Again, average potential energy per unit volume is going to be 1 by 2 of half rho omega square a square. Okay? So total energy, average total energy will be what? Average total energy will be average potential energy plus average kinetic energy. So what will be that? Total energy average per unit volume is equal to kinetic energy per unit volume average plus potential energy per unit volume average. Okay, so average is 1 by 4 rho omega square a square potential energy. Kinetic energy also same. Okay, so there will be 1 by 4 rho omega square a square plus 1 by 4 rho omega square a square. So total energy average is half rho omega square A square joule per unit volume or joule per meter cube. Okay, this is the energy carried by wave in string. Alright. Okay, now let us see in string where potential energy is maximum, where kinetic energy is maximum. Okay. So if I make a wave, okay, this is a wave. Now in this one, where potential energy is maximum, where kinetic energy is maximum. So first of all, I am writing the formula, the general formula. Kinetic energy is half dm into E square. And potential energy formula is, it was half T dx into dy by dx whole square. General formula I am writing, I am not writing half rho omega square A square. Okay, fine. So let us choose the points over here. So this point A, or this portion A, this portion B, and any other portion also we can check. Let's just see. Okay, why like this a portion? Because this will have mass dA. Okay, now let's go at this point. You tell me what is the velocity of the particle here. Velocity of the particle at A is actually 0. Okay, velocity of particle at B, max. Velocity of particle at C, somewhere in between. Okay, between maximum and 0. Alright, so where kinetic energy is maximum? No doubt at B. Kinetic energy is maximum at B. Minimum at A. There is no doubt about that. Why? Here velocity of particle is 0. Here velocity of particle is maximum. This is at mean position. This is at extreme. Okay. Now let's talk about potential energy. Now see potential energy. This is the length. This dx. This is tension. And this basically is slope. dy by dx means what? Slope. So we are going to check in this one where the slope is maximum. Now check at A first of all. At A, if I make a tangent over here, this tangent comes out to be parallel to x-axis. So that means slope is 0. Slope at A is 0. Slope at B, make a tangent here. This is x-axis, this is the angle. Is this the maximum angle anywhere? Answer is yes. This angle is maximum. The slope here is maximum. What about this point? This point also having slope, but certainly it is less than this. Okay, if this is theta and this is alpha, theta definitely is more than alpha. So slope is maximum where? At B. At A slope is 0. So potential energy is also maximum at B only, whereas potential energy minimum is at A. So in a wave in string, potential energy and kinetic energy is 0 at the same position, and potential and energy and kinetic energy are maximum also at same position only. Okay, is that clear? Alright, let's see then power. What is power? Power is energy per unit time. Okay, the energy carried by the wave per unit time is called power. Power carried by wave or power transferred by wave. Power. What do you write? Energy carried by wave per unit time. Okay. So what is the energy carried by wave? The total energy, we know per unit volume, right? That is half rho omega square A square. And this volume also you take that side. Total energy is half rho omega square A square S dx. Okay, now power we are writing. Power is total energy carried per unit time. That means half rho omega square a square s dx by dt. Okay, the time is over here in the form of dt. Now dx by dt means what? Velocity of wave. So change it, half rho v omega square a square s watt. This is the power carried by wave. Okay, now let us go for another term that's called intensity. What is intensity? Intensity is power carried by wave or power transferred by wave per unit area. Intensity represented with I. Okay, power transferred by wave per unit area. Okay, intensity is power by area. Power is here by S. What we are going to get? Half rho omega square a square into velocity. And what is the unit of this? Watt per meter square. Okay, it is watt per meter square. This is the intensity of a wave carried by string. Okay, intensity of wave carried by string. Okay, so these are the basic terms of a wave. So we have learned wave equation, velocity of wave, energy carried by wave, power carried by wave, and intensity of the wave. Alright, so this is it for this class.